My name is Emil Lundin, and I will now be presenting the Unicorn 2020 iteration with Christian, Anton Sundqvist, Emil Gustafsson, and Christopher. And so, as you might know, this is the third year where Unicorn has been a part of the project course, and we are very much happy to continue that tradition. And so the agenda for the presentation today then is to first and foremost talk about the background of the project. Then I will speak some about the project management, and then we'll talk about the dependable systems aspect, and finally the development. So the first two sections will be about bureaucracy, so please don't fall asleep. So the background of the project. The ultimate goal of the Unicorn project is to achieve sustainable, peaceful, and efficient robotic refuse handling. And it's a collaboration between Mälardalens University, Chalmers, Volvo, Husqvarna, and some other stakeholders. Whereas Chalmers is the head coordinator of the project, and MDH is only has the task of delivering a subsystem to Chalmers, which is supposed to be a robot with the capability of navigation, path planning, and object avoidance. And so in this iteration then, our goals was to create a working prototype, which should then be ready to be adapted to outdoor environments. And so with that said, the platform was supposed to have a working docking procedure, a working navigation localization, a improved obstacle avoidance, and some safety features. And so in this case, we limited the scope to indoors and to a known but dynamic environment. And we also focused on the reliability aspects. Now I will talk about the project management aspects. So first I will talk about some background. I will do so in order to prevent some confusion. And after that, I will talk about the Unicorn 2020 case. And so all claims that I do is basically based from this book. It's a very good book. I would recommend anyone who aspires to become a project manager to pick this up. And I would like to thank Henrik Falk very much for recommending it. It's a very good book. And so, as I said, I want to prevent confusion. And so I've countless times heard people not being able to distinguish between agile methods and project management. And so project methodology is a framework which dictates how project is managed, so in terms of organization and leading, whereas agile methods is a collective name for flexible methods, and it's a development method. So the key differentiator here is that the project management dictates how you lead a project, whereas agile methods is used to create results and delivering results. And so agile methods then is based on a set of values, principles, and attitudes, and it's inspired from Lean. And so agile project management is basically the combination of both project methodology and arbitrary agile methods. And when you combine those, you can create very flexible ways of carrying out your project. And so that is essentially what we've done. And so in agile project management, you use the project management methodology to get better overview and structure, whereas agile methods is used to organize daily work, handle requirements, and execute the project. And so usually the agile methods are used mainly in the implementation phase. So as I said, we went with a agile project management approach, and some of the most core principles of agile methods is that you have self-organizing teams, so you decentralize the decision making, and you also have cyclic processes, so you can frequently deliver results. And 3 out of 4 points in the Agile Manifesto is the one depicted here. And so you prefer working software over extensive documentation, you respond to change over sticking to a plan, and you also prefer individuals and interactions over strict process and tools. And I want to mention these because those things heavily influence the project management of the Unicorn 2020. And so this is the organizational structure, as I just mentioned about the self-organizing teams. We had two different teams. So we had one for the dependable students and one for the developers. And so we have the team leader, Anton Sundqvist and Christian. I would also like you to bear in mind that, as you can see, we have a lot of software engineers. And so we had a very solid software team. And I will talk about that in a couple of slides. So generally, every project basically follow the same structure. And that is, you have a pilot study phase, you have a planning phase, you have an execution phase, and a closure phase. And so then the only deviation from this general model in our case was that we only derived functional requirements at the beginning and technical requirements during the implementation. So this is mainly because of there's a lot of uncertainties in terms of research projects. And so since you're not too familiar with the topic, it's good to wait with the technical requirements and create those once you have accumulated enough knowledge. And so in order to enter a new phase, we used points of decisions, which is essentially like a threshold where you have to satisfy a set of requirements in order to advance. And this is to make sure that the purposes of the phases has been satisfied and so that the project is mature enough to continue. And so obviously, as the name suggests, with the first phase, the pilot studies, you write pilot studies, and you do so in order to reduce uncertainties and select solutions. We also define the scope, so we derive some preliminary functional requirements. We also, since we were given a already existing platform, we spend a lot of time actually investigating what was working and what did not work. And then we also analyze the given conditions. And so what that means is essentially determining whether the project is feasible given the budget and time. And so in our case, we did so with the use of a SWOT analysis, which is essentially a way of identifying the strengths, weaknesses, opportunities, and threats. And I will not bore you with discussing this in great detail. The only thing I want to say is that we came to the conclusion that it would be feasible project because we had already existing equipment and hardware. And so that is why we had a very solid software team, because we could use whatever was existing already. And this was a way of dealing with the limited timers in budget as well. And so that is mainly why we only have software developers, because we made use of the already existing gear. So when it comes to the planning phase, the thing with planning is that there's a wide variety of different opinions in terms of planning. So you have some project managers which argues that planning is the most vital part of anything, whereas other project management managers argue that it's unrealistic to plan. It's just a waste of time. And so if we go back to the manifesto, they state that you should rather respond to change rather than sticking to a plan. And so in our case, we use something called rolling wave planning, which is a way of planning in waves. And so you basically only plan in the near future, and then you plan multiple times in order to respond to change. And so in our case, during the planning phase, we had a very short planning phase. It lasted for only 1 week. And at the beginning, we created a work breakdown structure, and then we created a product breakdown structure. Now, the thing here is that plenty of people think they are the same, but you can have both if you make sure to differentiate the purposes. And so the work breakdown structure is a way of identifying all the work that has to be done, whereas the product breakdown structure is a way of deriving requirements. And so since we had an already existing platform, we could use a product breakdown structure to derive some technical requirements. And obviously the network diagram, it's just a way of, when you have identified all the activities, you form a logical flow of order in which the activities has to be done. And the thing with those is that network diagrams and work breakdown structures usually become very messy and crowded. And so in our case, we relied very heavily on the milestone plan. which is just depicted milestones, which gives you a better overview of what's actually happening. And then we created a delivery plan. And so this is the delivery plan. It was just a way of using the milestones in order to derive what kind of deliveries we should do and when. And I will not talk too much about this right now. I will come back to this at a later stage. But before I do so, I will talk about the implementation phase or execution phase. And so, as I said previously, I usually use agile methods during the implementation, and we did so in this case. And we used an agile framework called Crystal, which is based on 2 core beliefs. The first is that teams know best how to optimize and improve. And second is that every project is unique. And so the self-organizing teams know best how to deal with their work. And so Crystal consists of multiple methods. As you can see to the right, the thing was the founder of the Agile framework, he did not think that there was a development which suited everyone or any size of a project. And so within the Crystal framework, you have 5 different methods. So you have crystal clear, yellow, orange, red, and maroon. And the choice of those depends on amount of people and the criticality. And so, the more people you have in a project, the more structured and organized you have to become. And so the ones to the right is then way more strict than the one to the left. And in terms of criticality, it refers to the system crash. So in case of a comfort level, if the system crashes, that would lead to the user experiencing just a loss of comfort, whereas the life would refer to a system crash leading to a potentially death. And so obviously some processes need to change if you deal with a different criticality. And so in our case then we used Crystal Clear. And Crystal Clear is essentially human powered, which means that it's flexible and it's tailored according to people. It's adaptive, so you have no fixed tools or processes. You basically adopt everything that the team needs rather than having at the beginning. And so it's also ultra light, so you try to keep documentation reporting to a bare minimum. And so Crystal Clear is constituted by 7 principles. The first 3 are mandatory, whereas the 4 remaining is just for more experienced teams. Frequent deliveries obviously mean that you deliver the product often. Reflective improvements means that you have to reflect on what can improve in order to improve. Osmotic communication means that the developers have to work in close proximity such that they can ask questions and get feedback immediately. Personal safety is about, you should be able to criticize anything without ever feeling dumb. So it's a way of ensuring that critique is coming, basically. And so focus is just, you have designated hours a day to have uninterrupted work. Easy access to expert users is a way of ensuring that requirements are always up to date. And technical environment refers to automated testing software and the availability to actually have multiple developers writing code simultaneously. And so in our case then, we adopted the following tools and processes. So daily scrums, Kanban boards, and then we also adopted some lean principles. And so the first is delayed decision making. And so the thing with that is, usually if you take a decision very quickly, you usually base it on assumptions, whereas if you delay the decision making, you base it on knowledge instead of just assumptions. And the eliminate waste essentially refer to the progress. And so you will always save much more time by just not doing unnecessary activities rather than try to code fast. And so the implementation phase then, it lasted for 7 weeks. And so you can see the image to the left. We broke down the 7 weeks into 3 different deliveries, whereas one of the sprints had an additional week. And during each sprint, we had the planning, development, and demonstration. And so the planning then, as I said, one of the key principles is that you respond to change rather than sticking to a plan. And so every time we planned, we took those activities that was not finished and we prioritized them yet again with upcoming activities. And we did so with the priority system called Moscow, which is 4 levels. So you have must, should, could, and won't. For that we synchronized the tasks, gave ownership, and broke it down further. And then we estimated the time of the things. As I did demonstrations then, it's a way of ensuring frequent validation of requirements. It's also a way of ensuring frequent integration. And in case of a big issue, we could always revert back to previous iterations in case there were some very weird issues going on. And so, as I said, I would return to this. And so here's the delivery plan. So we developed the platform in a adaptive cyclic fashion. And so as you can see in sprint 1, we created a prototype with a complete lift, but only a draft planner and draft localization, which was not intended to work. Whereas the second prototype should have a complete navigation and also a good picking routine, or working picking routine. And then the last sprint, we wanted to create the robot and give it an emergency stop while also having a complete intention system. And then the fourth sprint was just, the things that happened afterward, after the deadline of the implementation. So finally, the closure phase. So the purpose of the closure phase then is to collect the accumulated experience. And we did so by using anonymous surveys. And so from the surveys, we could derive the following conclusions. Less time would be beneficial to put some time from the pilot studies into the implementation. More meetings during the implementation and more structure could have been beneficial. The pilot studies should also cover more details. So what I mean by that is, the pilot studies were good. We find solutions and stuff like that, but we never talked about the topic of compatibility. And so if we would have addressed compatibility in our pilot studies, we would potentially have saved a lot of time. And so pilot studies could also have been developed in a cyclic fashion using agile methods and cyclic processes. And obviously, since we only had 7 weeks, 2 weeks is quite a short time. And so if we could have a longer time, those sprints would have been extended, and that would have been very helpful. And we only had one testing platform, which was equipped with the gear that we used, the Roborio and the TX2. And so the issue is when you have 6 people that are trying to develop things, they might need to test their stuff on the platform. And so essentially the lack of, so only having one testing platform led to a bottleneck, essentially. And so here's just a rough outline of the timeline. And so you can see the first pilot study phase, it was conducted during 5 weeks, a planning phase 1 week, the execution phase 7 weeks, and finally the closure phase for 5 weeks. And so with that said, I would like to give over the control to Anton.
Yes. Let's see. Okay, so my name is Anton Sundqvist, and together with Emil Gustafsson, I will speak now a bit about what we did in the Dependable team during the implementation phase, during the project phase of this project. So starting with system safety, the goal of the system safety process was to manage and manage and control the hazards of the design we created on the Unicorn that could cause injury to people, environment, or equipment. So to do this, the system safety process consisted of 7 different steps. The steps of this process was first define objectives. In this step, we decided how safe should the Unicorn be, and what functions and attentions to safety shall we have on the Unicorn system? The second step, system description, is a step where we define our system, define the boundaries and the definitions of each system component, so we know where our hazards can be. So we need to know what the system is to define and capture our hazards. In the hazard identification and hazard analysis, we perform some different methods where we find our hazards and analyze them. In the risk mitigating measure, we try to decide on how should these hazards be resolved, and what actions can we take to solve them. In hazard control, we control the hazards, and then in verification of the controls, we control that the system safety is completed. And each step of this process is dependent on each other, so it needs to be done in order. Then the analysis methods we used for this are the that is supposed to say preliminary hazard list, not analysis. And this is our first preliminary analysis we do, where we brainstorm a bunch of hazards and try to just capture hazards in a preliminary way, not in such a formal way, just to get a sense of what hazards are present on the system. This is then transferred to the high-level functional hazard assessment and the system functional hazard assessment, where we look at each hazard in a more formal way. So in the high-level functional hazard assessment, we look more at high-level functions such as navigation or mapping, for example, while in the system fall hazard assessment, we look at more individual system components, such as the lift or something like that. So what would happen if we lose control of the lift, for example? And in the common cause analysis, we look at the independence, that independence exists between each component, so that no component would result in the failure of another component. And in the common cause analysis, we do some zonal safety analysis, and where we look at different zones of the system. The zones we looked at was the lift of the Unicorn and the electronics compartment, the automover body. And each of these analyses has a different aim in how we identify and analyze each hazard, but they lead to us getting some safety requirements that are later implemented into the development of the Unicorn and transferred to the requirements manager. And so for our requirements, they are essential to our project, and it describes the scope we set on it. So for this project, we had a list of 15 requirements that we served as our high-level requirements. And these were the functions we wanted the Unicorn to be able to have to be a complete system. So our goal was to try to fulfill as many of these high-level requirements as possible. And I believe we fulfilled most of them. And the requirement management work consisted of producing the requirement management plan that laid out how our requirements was supposed to be created, and the process of that work. It also has a workflow description that I will show a figure of later. But the main part of the requirements management work was the requirement specification document, where we have displayed of all our requirements and their attributes. So each requirement was given a unique identifier to relate it to a function or a part of the system. So for example, if a requirement was related to robot navigation, the ID for that requirement would be RobNav1 if it was the first requirement for that part or function. then to have a traceability to high-level requirements, each derived requirement from this high-level requirement would have the same ID, but so a derived requirement for RobNow 1 will be RobNow 1.1, and so forth if we derive the requirements further. So this would give us traceability to high-level requirements, and also in this document we had a status of what our requirements were. So if it was in development, if it had been approved by the review board, or if it was in the final stages of being complete and tested. So here is the requirement process. You can see the figure on the right. It's quite complicated, so I won't go through it all. But it shows how our high-level requirements they are elicited from customer specification and then derived into several functional and non-functional requirements, and also that the system and the safety requirements are present in the model. What is common for all requirements is that it must pass a review, where the review looks at several things of the requirement, that it's clear, that it's testable, and that it's relevant to the project. If a requirement fails, it can either be rejected or sent back for being changed by the requirements manager. Yes. So looking at the quality management, the quality management work was divided up into 3 different parts, and they happened simultaneously or at different stages of the project. So firstly, we have quality assurance. It was a way of preventing mistakes, and it was primarily used in the beginning of the project. And the main part of quality assurance was to have structures in place for our work, for our team's platform. So it's structure in the file system and guides for how things should be done. So there are methods and processes. We also had some quality metrics that we measured. So we measured how what the time was spent on in the project. So we had a time chart where we tracked what work was being done on. So if work was being done on navigation, and how much time was spent on that, so we could take decisions on if we should move more people over to that section of the development, or if we needed to change something. In the quality control stage, we use this plan, do, check, act model, where in each sprint we start with a planning phase and then did the sprint, checked it by doing a demonstration in the end of the sprint, and then acting upon problems we discovered during this check, or if we had any problems during the sprint. We also performed several reviews of requirements, design, implementation, and the testing, and also of the documents we produced. And this followed a template we created. So if an item was sent in for review, it could be approved or it could be sent back for revisions. We also did some audits where we checked on the development process. And this audit was done through a survey where each member anonymously answered what he thought about the development process and if something could be added to it. And lastly, quality check was done in the closure part of the project, where we checked on the work we had done and that we had fulfilled the customer requirements, and this was primarily done by testing. Now I will give it over to Emil Gustafsson.
Yes, so my name is Emil Gustafsson. I'm going to talk about the validation and verification process. Wait. How do I go backwards when in control? All right. Thank you. Yes, so to ensure and safety is fulfilled within the development of the project, validation and verification is used. Validation and verification aims to ensure that the design and implementation of the project is correct according to the requirements. The figure on the right is the V model that was utilized in this project. This model describes the process of performing validation and the different stages of it. Validation was performed before the implementation stage and was performed by different testing on different levels of the system. This is firstly performed on system level requirements, then subsystem level requirements, and then item level requirements. This is to ensure that the design of the system is correct and tested on the system before testing it on subsystem level. Because if the design is incorrect for system level, it will also be incorrect for subsystem level. Verification was used after the implementation stage and aims to ensure that the implemented product is correct according to the requirements. This was performed by first item verification testing, then subsystem verification testing, and finally system level verification testing. This is to ensure that items implemented are correct before testing subsystems, because if items are incorrectly implemented, then subsystems won't work. This process was carried out through 3 sprints, like Emil discussed earlier, where for each sprint, validation and verification was performed in the project. Validation testing was performed at the early stages of the sprint to ensure design was correct, and the verification testing was performed at the end of each sprint to ensure that the system developed during that sprint was implemented correctly and working. For this, testing needed to be documented, and this was done through a master schedule. Master schedule documented all testing activities that was to be performed during each sprint. It states relevant information about the testing, such as what methods used and what requirement is tested. And when testing was performed in the master schedule, it was then carried over to a validation matrix and verification matrix. Validation matrix for all validation testing and verification matrix for all verification testing. These matrices have a more detailed explanation of how requirements should be tested. It mentions things such as methods used, actions and order of actions to perform testing, and the expected tolerance of the system according to the requirements. In these matrices, the result of the testing was also documented. And one more thing about master schedule is that it referenced the other dependable work, such as safety, quality, and requirements. It mentioned the source of requirements as well as safety risk level for each testing or test case, and approval of the testing according to the quality manager. Next. So for the testing of validation and verification, multiple methods were used, and they were different for validation and verification. For validation, methods such as modeling, simulation, traceability, and analysis was used. Modeling was used for hardware requirements and was performed by creating a model of the system, which described the parts in the system, connections, what data is used, and the volt and such. These models need to represent how the system should work to act as a valid validation evidence. Simulations was used for software in the system. The simulator used was developed or used in the previous iteration, and it was further developed during these iterations to improve testing and testing for the software. Simulations allow the software to be tested either individually or with other software programs, which was used to identify if they work together and any problems when working together. Traceability was used for high-level or system-level requirements. This was used by analyzing the subsystems contained in that system. So if the subsystem in the system fulfill a requirement, then this is also true for the system level. This was useful in the project for requirements that was broad and covered in the different sprints performed. Analysis was used for safety and validity of data. Analysis performed was FOA and system FOA, which covered some safety-related requirements. Validity of data was analyzed also to ensure that data was correct to the design and the requirements. Verification methods used were inspection and demonstration. Inspection focused on non-complex hardware requirements and was performed by ensuring that the hardware was implemented and it fulfilled its function. Demonstration/testing was performed on both hardware and software, and were used or were performed by performing a demonstration of the functionality of the system or testing of it. This was usually carried out through a test case. Test cases was used to identify the minimum required functionality for the system to ensure that it works according to the requirements. Yes, and then now Christian and Kristoffer will talk about the development of the project.
All right. So my name is Christian Mortensen. I will talk a bit about the development of the Unicorn together with my colleague Kristoffer Lindve. So this year we were fortunate enough to inherit a robot with most of the hardware that we needed already in place in order to achieve our goals. So it's built on top of a Husqvarna Automower research platform, which acts as our mobile base with wheels and motors and all that stuff. And we also have two Pepperle plus Fuchs lidars, an R2000, which is placed at the front with a 360-degree view, which is used for navigation and localization purposes, as well as an R2100 placed at the back, which we use for our docking routine, which we'll discuss later. Along with this, we have a SED stereographic camera at the front, which we also use for navigation by incorporating it for obstacle avoidance. We have a NVIDIA Jetson TX2 board, which is our main computational device, as well as a National Instruments RoboRio, which mainly interfaces with the lift. Along with that, we have some additional stuff like a power distribution board, which was provided by a previous iteration. So we only did some minor hardware additions this year, where we mounted an Intel RealSense camera at the back above the rear lidar, which we'll also use for docking. We swapped out the swivel wheels, which came with the Automower, to omnidirectional wheels in order to reduce random rotations that we were getting. And we also implemented a wireless emergency stop to stop any motion of the automower or the lift if pressed. So development was almost entirely focused on software aspect this year. Developed the software based on Robot Operating System, or ROS, which handles the communication between all our software processes and between our TX2 and Roborio. It's an open source framework, which a rich library of many software packages that implement common functionalities for mobile robots. And as such, we could focus on the important parts, which we deem to be important at least. So we have there's a lot of areas. We will go over some of them in this presentation, and it will be pretty brief in order to save time. So we improved the simulator, as Emil said previously. We revised navigation localization. We implemented a docking routine to be able to align to and approach refuse bins to pick them up the lift. And in order to do that, we also had to revise the lifting procedure. And we implemented a prototype object tracking algorithm, which in future could be integrated with the navigation to better avoid the dynamic obstacles. So the docking routine is implemented in order to have the robot approach what we call a docking or a bin station, refuse bin station, which you can see here on the picture. Just consists of a piece of wood with some legs and a hook where we place the refuse bin, as well as a printed April tag on a piece of paper that we fasten with the tape. So the goal is for the navigation part of the robot to move to a position somewhere in front of this, and then trigger this docking routine, which I will explain now. It consists of 3 phases. We have an initial docking action where we need to move the robot into the correct position to align it pretty much perfectly with the bin, so the lift can pick it up. And the errors that are allowed here are pretty small. The allowed errors are pretty small, so it needs to be good. And then once we are aligned, we trigger the lift. And it can either pick up a bin from the hooks on the wall, or load it or unload it from the lift onto the hooks. Now once that's done, we do a final undocking action where we slowly move the robot away from the station in a controlled manner. And then the navigation takes over again. So here's a little video of how it looks. As you can see, the initial offset of the starting position was pretty big, so it's able to handle a lot of situations. So we use April tags to approximate the position of the bin, which is the paper below it. It gives us, with this position, we can approximate the distance and angle to the wall and move the robot in the correct position. And as we get closer to the wall, we activate the rear leader to get more accurate estimations of both distance and angle. And we used 2 PID controllers, which are manually tuned to regulate the velocity of the robot to approach the wall. We have one that controls the forward velocity, which is only based on the distance to the wall. And we have another one which controls the angular velocity of rotation, which is regulated based on the lateral distance to the center of the tag, as you can see. As you can see, as the distance decreases to the center of the tag, so the robot sort of straightens up. So the further it is away, the more it tries to move towards the center, and as it gets closer, it's more aligned to the pitch of the tag. And once the errors are within a given threshold, we activate the lift. And if that the error is too big, as it is close enough to the wall, we undock the robot and try again. Additionally, we implemented some features for in case an obstacle is in the way and is detected by the leader, we slow the robot down and stop it if it's too close. And as you can see, once it's close enough, it activates the lift and then backs out. And then the navigation takes over. So I'll hand over the word to my colleague Christopher to talk about some other stuff now.
Oh God, what did you do?
Oh no. You
Jesus
start
Christ.
the PowerPoint.
I surely can.
Did I break it?
Yeah, there. Can you hear me?
Yes.
Yep.
Yes, so the navigation, for this, our goal was to sort of revert back to tried and tested methods and use common ROS packages. And the point is to get sort of this part working, because everything else relies on having stable navigation to perform the tasks. So we used the common ROS packages that have been used a lot and that have shown good results. For comparison, if next year would like to change this and try their own methods, they can use that. But it's good to have a version of the navigation that is working, that you can always revert back to and use in the case something would fail. For the navigation, we use the MoveWaves package, which basically controls the robot. The global planner, we used A-star. The global planner is basically the algorithm that plans the path from the robot's starting position to the robot's goal. And it does this with a map. Meanwhile, the local planner is responsible for the local decisions of the robot. So when it's actually driving around, if something like an obstacle would turn up in its way, the local planner is responsible for acting on this and avoiding the obstacle. The local planner, which we used, was TEB, and it uses the LiDAR data and the camera to detect objects and get a picture of its environment. So the LiDAR was used to detect obstacles around the robot, while the Z camera is more used to detect high obstacles and low obstacles. For example, tables that the LiDAR can't see, or boxes on the floor that are lower than the LiDAR. And generally, from our testing, the camera gave quite poor results in combination with the local planner and the cost map. And it was also very CPU intensive. So this is a subject that should need to be explored a little bit more. You can see the video here in the screen. This shows the robot driving with the planner. The green line is basically the global planner, while the orange-red line is the local planner. It might be a little bit hard to see. And around every walls, you can see basically the cost map, and you can see a person walking into a room where a robot was. So for the localization, we used SLAM, more specifically G-slamming, to create the map. Slamming stands for simultaneous localization and mapping, which is a technique to create a map of the world around you. This method uses the wheel odometry and the LiDAR. We're also using this for part of the program part of the project to localize the robot, since we believe that previous years mostly used this method to localize it. And this actually worked very well, but it was very CPU intensive. So you have another version where you localize according to a predefined map, When you slam the map of the environment, you save it and then you use it with predefined map. And in this case, a method called AMCL, adaptive Monte-Carlo localization, is used, which is a particle filter. And this, in combination with the Wheeler geometry in an extended Kalman filter, is used for localization. And in general, this works very well, actually. But there are some issues with it that we also noticed during our testing. One of the main issues is if the environment changes a lot. For example, at one point we put a large box in the middle of the room and we told the robot to drive close to it. And this basically broke the AMCL algorithm and it couldn't recover after that. So it's not very practical in environments that can have large objects change. Our hope was that UEB would solve this problem. But we didn't really have UEBs at the start of the project to start testing with it in a way that we wanted to. So when we got the UEBs around December, we started by testing the design that we got from the previous year. The previous year had cited that they didn't get to work with citing the issue of transformation issues and then transform frames like they're used in ROS to put everything in place. So it wasn't very clear what the problem was. But when we tested, we noticed that the SLAM and the UEB, they both will create their own coordinate system, and the current slamming method doesn't have support for using a third-party coordinate system. And this, in combination with the UEB only having the Unicorn is only equipped with one UEB. And the UEB is not equipped with any magnometer or anything, so it cannot. With one UEB, you can only decide the position of the robot. You cannot decide the pose of the robot. So we don't know which direction the robot is pointing at any point in time. And this sort of makes it hard. So from our testing, we decided that the design of the UEB that we were handed is not a feasible solution. And we didn't have enough time to redesign the system and test it this year. So we put our manpower into other things instead. Yes, so for the object tracking, last year had started with object tracking with adding a version of YOLO to the Unicorn. And YOLO uses the camera to track. There was also a possibility of using the LiDAR track, not with YOLO, but with other algorithms. The issues when we were testing this method is partially that there wasn't really any tracking algorithm implemented for YOLO at the time. So they had added YOLO to the system, but it's just detection or classification algorithm. You can't really use it for much more. And the said camera, which uses this, has a very low viewing angle, and it is very CPU intensive. So it's not very practical because there are not very many objects that you can detect. Instead, we decided to try a prototype with tracking with 2D LiDAR, which has a very wide view, but it has very little information with just 2D point measurements. The basic concepts of tracking are a detection step, which detects objects and separates them. Since we're using LiDAR data, we're using clustering methods. An adaptive breakpoint detection is very common in LiDAR, which we decided to use. For association step, this is a step that tells you if one object in one frame is the same as another object in another frame. And in this, we use the similarity index. This is easily implemented, but it's not necessarily the best solution there is out there. This could be improved, but this uses the predictive precision and a shape extraction to estimate if an object, the probability that an object is another object. And for tracking, we used Kalman filter trackers, and these are Kalman filter based trackers, basically with each object getting their own tracker to track their movements. And this predicts the position of the tracker at each position of the object at each time step using a constant velocity model, which is basically straight line movement, constant y, and constant x velocity. A short video here showing the tracking in the simulation can be seen here. The tracking works that it is color coded, meaning that each object will get its own color. So this is a way to see if an object is if you are able to track an object or if you're losing it, for example. And then also when an object is moving, as you can see at a gray object, it's getting an arrow which shows the heading direction of the object. So some of the issues is, for example, with tracking that you will go around objects and they will change the shape of them and things like that. You have to determine if these objects are the same objects as other objects. Next here, you will also see an example of tracking when we are running on the robot. And this here is tracking when a person is walking around the robot. You can see two arrows here, and these are the two legs of the person which are being tracked together. And the robot mixes these up now and then, as you can see. For these objects that are close objects that are moving together, this is not actually an optimal algorithm. What you need to add on to this is a group clustering algorithm, which is very common for tracking humans with LiDAR, where you group certain objects together and you track them as one object. At the picture here, you can see an example of the shape extraction, where you have a line and you have a circle right in front of the robot, and on the other side you have sort of an L shape, which is what you get when you're tracking things with a rectangular shape. Some of the issues we experienced with this was with the localization, which is very important for tracking. If actual movements cannot be decided from the localization, then it's very hard to track objects when the robot is moving in the platform. This was not an issue with the simulation, only in the robot, which is because the odometry in the simulation is next to perfect. We also had some issues with the CPU usage, which is not necessarily tracking problems, and synchronization, which is a problem with tracking algorithm. The design of the algorithm would theoretically allow you to, which would have been the next step also, to add another detection method, such as YOLO, which they had added in a previous iteration, and combine this in as another detection step. Because the only step you basically need to redesign is the association step that decides which measurements belong together and how they relate to next frame. And adding a camera to this would greatly increase the capability of association, especially in harder environments. For the future work, there are a lot of objects that we have mentioned in the report that needs to be done in the future work. But some of the main points that we also have discussed a little bit here are the UVB, which we would love to see them working on the Unicorn, and we have seen the possibilities with this. But redesign the UVB setup to allow for pose estimation with the UVB. The UVB could also be used for other things, such as localizing the refuge bin or communications with multiple robots. Another thing that we were discussing in this project was using fuzz PID controllers, which have generally provided much better performance than normal PID controllers, which we're using now for the docking stage. And this might be an interesting thing to test and compare. And then also adding close-range object detection sensors, such as ultrasonics, to detect low obstacles close to the robot. Because even the camera cannot detect objects that are very close to the robot, and it wasn't doing a very well job in detecting objects otherwise also. So sensors like ultrasonics would be really good to add to robot. Also, this would also allow the robot to detect transparent objects like windows. So if you had a glass door, it wouldn't run into it. And the last point is integration of the tracking into the navigation algorithm, which would improve the tracking capability of it would improve the navigation capability in environments with dynamic obstacles. This is something we looked at, but we didn't really have time to do it.